Can you all see?
Mm-hmm.
All right, let's get into it. All right, so this is, sorry everyone, part 3 of the error surfaces and lost landscapes. So I think we are recording. And then one thing is, so first of all, the slides I posted into the Slack channel in the agenda. So you can go through with us and hopefully the links work. I'm pretty sure they do. So you should be able to get to all the GeoGebra activities, but if you can't, all the titles will be in the tab. So you should be able to find them there. And then again, I just wanted to thank you guys for letting me do this. I like this, and I forgot last time, but I want to give Danya a shout out because she hates this, but she's helping me like practice, and a lot of this is her ideas too. So she just doesn't like presenting, but I figured she's hiding her face. Okay, so all right, so I wanted to do just a quick primer. I think this part might not be quite as fun, so I'll probably go a little bit faster, but I think some of it's important. So I think there's 4 slides of it. So the first thing is the loss surface, just to say it clearly, the loss surface is the thing that you're trying to minimize during training. So I think we've probably said that implicitly, but just wanted to say it out, right? That's the point of it, is it's the thing you're minimizing during training. And then, people talk about a network's capacity. And all that is, in the context of loss surfaces, is how close to 0 the minimum of your surface is. So if you're looking here, this one has great capacity because its minimum is at 0, right? And then one other thing to think about is when you're looking at these loss surfaces, and if you're looking in weight space, you can think of a model as a point in weight space, right? So if this little snippet here is in weight space, so like the x direction is weight 1, the y direction is weight 2, then a model is a point here, right? And so as you're trying to optimize here, once you get to like the argmin, the x and y of those weights is a model, right? So maybe this is the initialization point, and then you optimize and then get here. So each point in weight space is a model.
Hey, Grant.
Yeah, go for it.
Can I roll back to that capacity? I'm understanding capacity is how close the minimum is. I guess I think of a capacity of a model is kind of, it's related to the dimensionality of the parameter space.
Yeah, so I would think of it as like this, because if your model has more capacity, then it can learn better, right? If there's more parameters, right, then ideally it can learn more and get more accurate. And so that's why I would call this the capacity. You could probably think of it in a couple different ways, but this, I would say, is definitely one way to do it, right? I would think of like the weights as like the complexity, and I could kind of think of this as like a capacity. I think either way is probably fair. Would you agree?
Ted, were you unmuting to comment?
Yeah, I was going to jump in because it seems to me, along the lines of what Roger's saying, it certainly will correlate with capacity. I don't know that it is defined as capacity. Really, ultimately, that the lower your loss, theoretically, that should correspond to better accuracy.
Mm-hmm. Agreed. Yeah, so maybe this one's a little sticky. I'm glad I mentioned it. Okay, so next thing, just another slide. I know there's a lot of text here, but this isn't, it's not too complicated. Okay, so I was thinking, given a set of data, the architecture is equivalent to the loss surface, right? So if you change how many neurons you have, you change how many layers you have, that's equivalent to changing your loss surface, right? And a good architecture is one that corresponds to a loss surface with the following 2 properties. A, the minimum is close to 0, aka good capacity, or however you want to think of it. So it's got to have this property. And it also needs to be easy to train or easy to find the argmin, right? Or at least find a domain point whose loss is similar to that of the actual min, right? So speed, easier to find, is faster to train, and so on. Okay, so, and then down here, each of these points, these 2 things that we want, they're easy to get individually. So the goal is to get both of them, or to balance them, right? So the universal approximation theorem says we can always get a function that perfectly gets all the way to 0, right? And then, for something that's instantly fast, you could just have a constant network, right? So the goal is to balance those two things, is the speed of training and the capacity, or how close to zero you're getting. Okay.
So,
Yep.
sorry, another comment there.
Yeah.
So I'm thinking there's an attribute that has to do with generalization of the model to expand out, to the unseen data.
Yeah, I like that. Yeah, that's a good idea.
And we've talked about that in other meetups about it. If you look at it from a loss surface, you're finding a minimum that is, if I recall, we described it as kind of a flattish minimum. You're not looking for a highly, very narrow specific minimum, but rather something that's broader.
Yeah. Yep, absolutely. I think that's a great call. I think that would probably, I think that's a better way to say it than this, actually. Or yeah, good generalizability.
It's a third bullet. Yeah,
It's an interesting point, Roger. You definitely don't want your model to overfit on just the training data. So that would be a lack of generalizability, right? If it's overfit.
Right.
That might correspond when we're looking at the loss surface of like something with very pointy, small, many local minima, and you're not necessarily in the, the right one, the global one, right?
Right.
But then there is a separate problem of generalizability, which is not really, I don't think, loss surface related. If I train an image model on ImageNet, does it generalize well to detecting cancer on X-rays? That's kind of beyond, right? But it is a question people ask, because they say like, oh, if I do self-supervised learning, am I going to get more generalized features than if I do blah, 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 right? So I think there's the two different sides to that same generalizability question.
Right. I was thinking that the former, just within expanding beyond the testing into other data. I don't know what the correct term is here. Maybe you can help me out, but data that's in the distribution, but not specifically the test data set. And it's that if you sample data beyond that test data, but still in distribution at a loss surface level, I guess it'd be kind of how much does the loss surface change with these other subsamples of in distribution data?
Yeah, I like it. Yeah, so definitely some other things in this column here as well, or in this set. So generalizability, I think that's essential. And I know I'm going pretty fast on these, but just one more thing. So this is kind of just a question or a thought. So if we only have an affine or linear function, so we don't have the activations, then the loss surface is parabolic. And if we just have like ReLUs, in all of our toy examples, everything was either flat or parabolic. So I'm not really sure how we get such complicated loss surfaces, but of course, just more dimensions makes it look more complicated when you project it downward. But I'm curious if the loss surfaces actually are just flat regions and parabolic regions. And I don't really know the answer to that, but I don't know why it would be otherwise unless you use something other than a ReLU.
Grant, with the ReLUs and stuff, though, you're still looking at mean squared error loss, right?
Yeah, just in this example.
Right.
Yeah.
So that's why it's parabolic. You start using a different loss, and then you can get all sorts of other things.
Sure. And then the last kind of just prerequisite stuff is, and I don't know if everyone already knows, I'm kind of curious, but if let's say, we'll just start with this right here, this drawing is equivalent to this first row. So when we're building a neural net, if you just allow yourself weights and no bias and no activation, so that's kind of what I tried to draw here. So I have no biases, and then these are like the connections between, and if we have no activation function, this is equivalent to having no hidden layers and just having a linear function like this. And the drawing looks like that. And then if you allow biases, the same thing happens, but you also get that bias right there, right? So this whole thing just condenses into this thing, right? All those hidden layers get lost. And then the last one is if you also add in activation functions, then of course you can approximate any function. All right. Okay, so on to the material, and I think this is where we left off on in last week. So I want to tell this as a story, which I know is kind of goofy, but I want people to have the same feeling that I had when I realized it. So we'll kind of do it that way if that's okay. So the first thing was I was trying to train just a ReLU network on XOR data. All right, so like this is some XOR data, and I was trying to train a ReLU network on it. And I'm just going to this GeoGebra example here. So I'll just draw a couple points. So like here, here, and here. Maybe these are what we're trying to fit. And then A and B are our parameters, right? Our weights. Okay. And so when we had the data like this, you know, the network was trying to move these weights, right? And so if it's trying to fit all these, maybe, you know, this would come up like this or something, right? Maybe it would come around here. Okay. And so now maybe it would try to move this, but there's nothing it can do to fix this error right here, right? So it might move A and maybe it'll nail E like that, but there's nothing it can do to fix these other than move up and down. But in any case, you still have some error there, right? So I was wondering, you know, what am I doing wrong, right? Is there something I'm doing wrong, or is it just that it's true, like it was kind of hard to do? And I want to notice one other thing is that when we tinker with these, you know, this slanted part at the top right is what's moving most of the time, right? So I had always thought about like, this is the part that you have to tinker with your weights, right? This is kind of what you're training is this thing, and this thing's sort of like dead over here, okay? And so then I thought, you know, we need something that's easier to train. How about a linear function or with no activation, no bias, right? So I was thinking, you know, we could train that, right? Linear functions are easy to train. And then maybe we could add a bias and just have an affine function. And then maybe once we train on those, then if we like sort of turn on the ReLU, we would be able to fit what we wanted, right? So we wouldn't have this difficulty, you know, maybe we would just train it with linear first and then sort of turn that on. Okay, maybe that could fix it. But the problem is the minimizer would jump away from the point we found. And this was in one of the activities we did last week. So I'll show you what I'm talking about. Yep. So if we turn off the ReLU, so right now, this is just a linear function, right? Or maybe it's affine. But in any case, so if you find the min of this, which is easy to do, right? It's easy to find this min, so it would be right here, right? But now if we turn on the ReLU, all of a sudden the min jumps over here, right? So we can't just turn it on and off because like the optimization point, that argmin totally moves, right? So I was wondering, you know, maybe we could sort of gradually turn it on, right? So let's optimize right here. And then maybe we'll kind of turn on the ReLU a little bit, turn it on a little bit more. And as we go, we'll continue optimizing and just keep finding that point as it gets dragged over, right? So kind of like that, you'd keep optimizing. And then finally there, you will have gone there more slowly, right? But you will have found the minimum, okay? So I was thinking, you know, we need to somehow smoothly transition from no ReLU to ReLU. And so this is another little activity trying to show what it would be like, right? So here's a ReLU, and then here is no ReLU, right? So I was thinking, okay, we train like this and we go find our points, right, by moving these around. And then slowly we turn this on. And then we could do that optimization. Okay, so so I just want to draw what I was kind of thinking about, right? So let's so we have, let's draw our original, just a neuron, right? So we've got the neuron, the input, and then we've got the connectivity, right? And then we've got So this is sort of our ReLU right here, right? This is a ReLU. Okay. And so what I was thinking was, you know, instead of this, maybe we could sort of like, when we turn it on, how would we draw that? How would we draw that diagram? Instead of having all of this already linked up, maybe we want this thing to sort of, right? This is like an identity function, right? So ID instead of the ReLU. And then maybe this does what? It kind of like connects here. So does anyone see what that is?
Is the ID the R that you just shown?
The ID is the identity function, right? So the identity function would be like, if this thing is off, right? This is the same thing as an identity function as your activation, right?
Yeah, got it.
Yep.
Thank you.
Yeah, good question. Thanks, Julien. Okay.
So I don't know if I understand this diagram that you're showing right now. We have this thing called leaky ReLU, and you can have very leaky, and you can go all the way between very leaky to full standard ReLU, but I'm not quite sure what this diagram means.
So that's a, yep, that's, I know where you're coming from. So that's not exactly what I'm trying to talk about. So this right here, this drawing, this is a residual connection. Right? So,
oh, okay. Okay. Yeah. So you're talking about whether you use exclusively the residual path and then gradually you weight more and more of the ReLU path.
Right. Yep. So the thought experiment in GeoGebra would be, this thing is turned off at the beginning and you have full of this, and then over time you could turn this one off and the ReLU on, right? But that's the same thing as just having a residual connection and training it. So this thought experiment we just did about, like, you know, having partly a ReLU and partly an identity function as your activation, that is exactly what a residual connection is. Does anyone buy it? Confused? Thoughts?
I buy it. At first, I just didn't understand the ones, but those are your biases.
Yeah. Anyone else? Residual connections. So this is our drawing, and this is the drawing of a residual connection. Sometimes they skip both, sometimes they skip individuals, right? And so my whole premise, I had never read this. I like stumbled into it, right? So the premise of this being easier to train and this maybe giving the residual connection gives us, it makes it easier to train, but it also gives us the same capacity, right? Isn't that the idea of it? So I think this is how residual connections work. So I was pretty shocked when I noticed that, but so should I go to the next slide, or does anyone else? I feel like I see wheels turning, or fire away if so.
My understanding is the residual connections are especially helpful on deep networks.
Mm-hmm.
It avoids, it's been described different ways. Sometimes it was kind of the gradient highway that allowed you to gradient way down into the bottom. But I think another way to look at it is it kind of helps to control exploding or vanishing gradients, because it's essentially a constant, constant one, and so the parameter space can be lower magnitude, and so you get smaller swings. But it would be, the way you're drawing it, it kind of looks like normally the residual is not fed directly into like that.
Well, these are added together, right? This plus sign, that's exactly what we're doing in this activity.
That's a plus. Okay, and
yeah,
where your weights are the
A and B.
On that other graph, the weights are on the edges. Is that what you're?
Yeah, the weights are on the edges. Yeah.
So there is not a weight then on the edge between the ID and the sum?
Yeah, so I think that's probably a little hand waving. I think that's maybe not as, I don't think that's particularly as important. I just think the connectivity is kind of the same between them. Yeah.
If you throw in a factor of normalization, then you could always fix the ID at 1 and then just make the ReLU bigger or smaller to match, right? So if originally the ID was 2 and the ReLU was 8, then you could just shrink the ID to 1 and make the ReLU 4, and you'll still have the same relationship. So I think that would be sort of a non-hand wavy way to say that you can always normalize it such that the ID path has weight 1.
Yeah.
That original, you started by saying that it's hard to fit. Like you had 3 data points and it was hard to fit the 3 data points.
Yeah. These in particular on this dead area.
Yeah, so my read on that would be that the problem is that you have essentially a single ReLU here that you're controlling, right?
Yeah,
so
that's fair.
You don't have enough, what I would call capacity in the model, include all 3 points. You're either going to have an error with the model that you have, or you need a more complex model because you need more wiggles in that line. And I actually don't know if it's more depth or more width. It might be more width that you need.
Okay. So I think I can actually answer the question.
Okay.
If you want. So here's that. And so what I wanted to do was find sort of a middle between them. And so introducing here for the first time ever, the RelTwo. So what this is it's a ReLU, but this, instead of just X, it's half of X. So it's basically halfway between the identity function and the ReLU. Right, so nothing too crazy, right? But I think it works from my little experiment. So let's just go right here and let's turn it on halfway. So this right here is a RelTwo, right? And so if I go ahead and draw those 3 points in there, am I frozen? Okay, no, I'm not. Okay, so let's do C, D, and E like that. So because we have a nonlinearity, we should be able to fit 3 points, right? We should be able to, because a linear function can only fit 2, but the nonlinearity should make it be able to fit 3. So if I rotate this around, nope, back the other way. Let's see. And this I'm doing on the fly, so please don't judge me. Oh, that's pretty close. Okay. Maybe I'll come over here a little. Not bad. So this RelTwo, since it's not 0 on that other side, it actually does have the capacity to fit these. And you can see, like, as I move these, this is pretty smooth movement, right? And then if I move A, again, this is very smooth movement. It doesn't feel herky-jerky to me, but if I make it just a ReLU, right? Now if I move our weights, like, see how now if I come over here, now that part's moving, and now this part's moving. So in my opinion, that makes it really hard for the optimizer to figure out the training. Right, and this whole reason that I'm showing about these being all weird, this is exactly why you have to do a residual connection, is because it can't figure it out with the ReLU alone. And I'm kind of speaking like these are facts, these are my opinions, but I think this is what's happening, right? And so I did a little experiment. Well, I just wanted a couple properties. So first of all, it's halfway between the identity and the ReLU, which I think is similar to a residual connection. And then dividing by 2 is super fast and binary. We just shift the bits to the right? So the computation isn't bad. And then I just showed kind of those function transform properties. And it's less nonlinear, so it's easier to train, right? So there's a couple properties there. And, a little side note here is I think the swish or mesh are harder to train than the ReLU because of the non-monotonicity, which I think is harder to train than the RelTwo. But judging by performance of like massive scale problems, my guess is the RelTwo probably isn't actually state of the art, but like I'm guessing that's a little worse performing than the RelUse's Swish. So it looks to me like these are reversed. Like the ones that are easiest to train perform the worst. I don't know for sure, but this, it just seems like that if I took a stab, which seems weird to me, but I don't know. So I did a little experiment. I wanted to do it on more complicated data sets. I just didn't have time, but I just used the RelTwo on this spiral data set. And here is the output of the network, which I thought was pretty good. Does anyone?
What was your network architecture for training that?
It's right here. So we had the two, like the X and the Y, and then, each layer, I just did 12 neurons wide, which for really no reason. So then we had 1, 2, 3, 4 hidden layers, and just had batch norm in between them, and it trained no problem, which I think is what's happening. I think it's easy to train.
And did you try any other activations like ReLU?
Yeah, this whole thing stemmed from trying the RelU and it didn't work.
This very same problem?
Yeah. Or at least I tried the XOR data set. Yeah, so not the same problem. I tried this data set and I was having trouble. I think part of it I fixed by normalizing. So when I originally did it, this was X equals 0 and this was X equals 1, which it actually couldn't train because it didn't capture any non-linearities in the ReLU. So once I normalized it, this was 0, this was negative 0.5, that was positive 0.5, and then it could train it, right? But if it doesn't have that non-linearity in there, it can't figure it out. But yeah. So it at least can do something.
I love the conversation. I'm not sure if I buy your argument. I'm not sure even what easy to train data points we have, because I don't know that people have actually tried Swish, ReLU, Mish on small problems to see if they're easier or harder to train.
Mm-hmm.
So like normally when people talk about easy with deep neural networks, they're talking about whether or not like the loss progresses nicely and whether or not you can get problems with like vanishing exploding gradients where like you'll get one random number seed that just it craps out and it doesn't actually converge, right? So normally when you see in a paper somebody says easy, they're not really necessarily meaning the same thing you mean by easy. They're sort of looking at like whether it's more consistent and faster to get to the convergent local minimum.
So just jumping. So if we want to, so if we design a new type of neural network and we want to prove that this is performing better, so either we can look at, hey, is the kind of like the loss decrease kind of like very smoothly, or just it just takes less time to train. And
yeah. Sorry, keep going. What were you saying?
Yeah, I just want to know like how to prove that your model is better than other people's model.
Oh, I don't know if it's better, or I assume it's not. I just, like as I was thinking through, it just seemed to make sense. And then, I tried it and it seemed to work at least a little. So I thought it was probably at least worth poking around some more. And, like as far as these function transforms go, like it, to me, I think this is pretty clear which one is easier to follow and which one the optimizer will have an easier time training, tweaking the parameters, right? And so to me, that's the same thing as trainability of like going down the loss surface. So that's my guess. But,
hey Grant.
Yeah, go ahead.
One question on the slide that you were showing before.
Yeah.
Training versus.
Yeah, this.
Yeah, this one, right? Yeah, I'm just thinking out loud here. What is this untrained network? Why do you have this spiral shape? What is happening in the middle?
Oh, this one?
Yeah.
Oh, that's, I mean, this isn't too significant. This is just showing like an untrained network. It can't predict it, right? It's just showing that it's basically all halves. So this is untrained and this is trained.
But were you not expecting like a scattered sort of plot as opposed to, I do see a spiral shape, right? Even though it's untrained, should it not be like all random?
No, these are just the same X values, right? You're training the predictions, not the features, right?
So it's a classifier which spiral it's on. Is that what the problem is? You got your X and Y and you're trying to, the output should be, are you on the yellow spiral or the black spiral?
Yeah.
I see. Yeah.
Does that make sense?
Yeah.
Yeah.
So how we need to interpret that middle graph is all the dots are where you actually tested the untrained network. And just because it's large enough, it has enough weights, it tends to randomize. And so we're going to get a lot of predictions that are just near 50%, halfway between yellow and black.
Mm-hmm.
So not really,
right.
Not really
a
prediction at all.
Grant, if you have this, if you have this available in like a notebook or something like that, Colab notebook or something, it would be interesting to kind of compare this with different activation functions and as Shulin said, you know, what's the time for it to converge, and also kind of maybe what's the predictability, how stable is it during that, the loss function during that time. And then you could look at different activation functions and actually try the true residual level layer as well.
Yeah.
Residual connection.
Yeah. Actually, it turns out I didn't look at the color code. So I missed out. This is it's 0.5, right? Yeah, it makes sense pretty much.
Yeah.
Oh yeah, right there.
Yeah.
Nice. Okay. Well, that's the last part on those activation functions. But so now kind of shifting gears a little bit, but still definitely in the flavor of like these error or loss surfaces, is talking about not the curse, but the blessing of dimensionality. So I've read, this is actually Danya's joke too, for the record. So I've seen a lot of like Medium posts and YouTube videos and stuff talking about the blessing of dimensionality. So kind of, and I took these things from a couple different presentations, which are referenced at the end. So it might feel like a little hodgepodgey, but I think the flow makes sense. But in this talk, the person was basically saying, you know, why does machine learning or deep learning work at all? Like it goes against most of our thoughts, like the curse of dimensionality. It completely ignores that, right? We way over parameterize, and same with Occam's razor. You know, like we want fewer parameters typically in most statistics, but yet we're way over parameterizing. So like the kind of, we're wondering why does it work? And one of the reasons that they were talking about in this talk was, you know, we've gone from finding a needle in a haystack, you know, trying to optimize and find this one optimal point that we've been looking for. But now since we've parameterized it so much, it's a haystack full of needles instead. You know, you can find a minima super easily, it's no problem. In fact, you can find minima that interpolate the data and literally have no loss on the training data, right? And at which point it becomes a problem not of finding the needle, finding an interpolation point or something that minimizes your training loss, but we want to find something that minimizes our test loss, right? So we can find a needle, but the question is it any good? And this fact of finding, you know, having a haystack full of needles, it makes sense to me with, you know, what we talked about last time of the low dimensional trajectories on our optimization path, because they're optimum all over the place. So you can essentially just go straight to it, is what I'm thinking is happening, right? And so then this is a different slide, but again, it's sort of talking about the same thing. So this is that linear path thing. This is what in the Goodfellow paper and is what I'm sort of talking about, right? So like when you initialize somewhere and you find an optimum, if you draw the linear path there, it actually turns out that there aren't like big ups and downs here. It actually does go down the whole way, but not quite as you know, as steeply as going the gradient descent path, right? As going this way. But in any case, you still can get there. And again, I think that makes sense with those low dimensional trajectories and sort of haystack full of needles. And on this guy, it's kind of a funny story. I'd read the paper and watched a Yannick video on the paper. And then I was also watching this video. And this is the guy who wrote the paper that the Yannick video was about. So I highly recommend this. This video is awesome. I can send a link as well. But it's talking about like geometry of loss surfaces. And there's a ton of other slides from this talk in here, so we'll get to those. And then there's one other thing called mode connectivity. Has anyone talked about this or seen this before? Okay, Ted, yeah, I see, yeah. So you can see this. This is from the video I showed the first night. But so basically what's happening is here's a minima and there's a minima over there. And if you look between them, there's this huge high area, right? So it looks like, you know, if you just look from a cross section between the two minima, it looks like there's this huge barrier between them to where these basins are not connected. But what people are finding is that if you just, instead of, you know, restricting yourself to a linear path, if you allow yourself a curved path, it actually, all these basins are connected, right? So you can see in this picture, you know, if you come along here and go around the other side, they're connected. And then here's another paper that was essentially written at the same time, and they found the same thing, right? You just got to go around, right? So it's pretty interesting. And actually, so this next slide is going to be fun, kind of funny. But so what this is the people who did these studies, right? So instead of going linear, they tried to find the path that would keep the loss low. They used those same methods. And they said, okay, let's take any random drawing, right? Can we find that drawing in this loss space? And the answer was always yes, in whatever they tried. Using those methods to find the connected path, they use it to find, they use it to find these other shapes. So these aren't things that people drew, these are actually in loss surfaces. So I was kind of shocked when I saw that. Yeah.
That is weird.
I know. I think I may have flashed this image in a previous, like maybe last week or something, and I didn't know what the picture was of. And then I continued reading between then and now, and I was like, oh, that's actually real loss surfaces. That's not just a drawing. But
what
kind of funny.
Did they say anything about what the models are that are producing these loss surfaces?
I don't know off the top of my head, but
Okay.
I have the reference in the link I can send for sure.
Yeah, I'd guess that anytime you have a billion parameters, you're going to have a lot of shapes. You know, it's like finding a face in the moon, or, you know,
yeah,
or you can find it somewhere.
Yeah.
That's a good question, though. I mean, how big does your model have to be to do?
Include Batman?
Yeah, to do Batman or the cow, you know. I don't care about the other two.
Yeah.
Yeah, I don't know if
here,
like
it says
the
it right
Batman
here.
and the cow are important, but this idea that, like, let's say you were just doing something simple like predicting house prices, right? And if you just upped things to where you had 1,000 inputs, a bunch of these inputs are going to be like multicollinear and redundant and this and that and whatever, right? But so you can imagine that if you found like any optimum point, there's probably going to be at least like one variable that if you change it, it's just not that important, or two variables that if you increase one and decrease the other at the same time, that you can keep pretty much your predictions and your loss like pretty much the same, right? And so it's just sort of like, if you're going to like crank one parameter up and the other down at the same time, can you just stitch together a number of these to get you between any two arbitrary points? And so, Grant, when you went all the way to the very beginning and you said, hey, look, like mean squared loss with a linear function is just going to be this paraboloid shape, right?
Mm-hmm.
But if you take a paraboloid, whatever, like we think of it, in 1,000 dimensions, then maybe it's got sort of like these huge flat ways that you can do this mode connectivity. And so maybe there actually aren't zillions of needles, to your analogy of the needle. Maybe in fact, it's just one ginormous needle that has all these different points to it, that's as big as the haystack, so that almost anywhere you look, you'll see part of the needle.
Yep. So I think, yeah, that's what I was thinking. So I think in a couple slides too, there's a little bit more on that same idea, because I agree. It is very, very enticing, and I think it's probably true to some degree. So yeah, that's this one. Yeah, go ahead.
One point. So does it mean, right? So on the previous slide, right, when you have direct path, or let's say our path, right? Our path meaning, of course, it's not direct or linear. So in this case, like Ted was saying, so does it mean that we are doing some sort of hyperparameter tuning to go from, let's say, a random path as opposed to linear path? Or does it mean that we are using a different optimizer or a combination of both? Or does it mean that we have a different architecture altogether?
It's just saying this is the optimization path, right? And
Right.
now that you know where you initialize, you know where you ended up, just draw a straight line between them. You're not optimizing a second time. Does that make sense?
Right, but let's say, as you said, right, in the next slide, so you have two basins, right? And in between you have this big gigantic thing, right? And it turns out if you change your optimization path, you can go around it, right? That's what I got from sort of the slide, this mode connectivity thing, right?
Yeah. So the word connectivity, what they're really talking, when they say mode, what they really mean is local minimum. So local minimum connectivity means that no matter what optimizer you choose, you don't really have to find the global minimum or a really good local minimum. If you find any local minimum, if it's kind of a crappy one, you might just be able to follow this curved valley if you train long enough to get to the next one that's a little bit better. Okay. And then eventually you'll get to one that's very good. It may not be the global minimum, but that's why with completely different random number seeds, you train it, you seem to consistently get very similar losses, even though we think you're winding up in different minima, right? And it might just be because like if you imagine like the Grand Canyon, okay? If no matter where you are in the Grand Canyon, I'm assuming it's like ever so slightly tilted since the river goes downhill, right? By definition. No matter where you are in the Grand Canyon, at some point you're going to wind up at the downriver end of the Grand Canyon if you follow the gradient long enough. Right. And so like what this is really saying is that if everything is this super high dimensional single canyon with lots of, you know, the Grand Canyon probably has like little offshoots, right? It's not just one V, it's got like side branches and things, right? So like if you were not you know, in a helicopter and had a map and whatever, you might say, oh, this is a very complex contour. This is a really gnarly looking thing. But like, we have enough that you can like zoom out and say, well, no, it's really just one V with a few side branches.
Right.
So that's really what they're saying about this is like, oh my gosh, maybe this isn't really a complex loss surface. It's just one giant canyon that's 1,000-dimensional. And so we can't really understand it. And therefore gradient descent kind of always works because it's such a simple, you know, it's not convex. The Grand Canyon is not technically convex, but locally it's pretty much convex everywhere. And they're all connected.
So is this saying that all of the local minimum are kind of connected through some path that doesn't involve a high loss?
Yeah. So yeah. So there's yeah, exactly what you said, Roger. Yeah.
Okay.
So like what they found was between any two, you could basically pick any two. You know, you start from a different spot, you get to a minima, you can find a low error.
Relatively low, I suppose.
No, like pretty much the same error, but
interesting.
So it's almost like they aren't like separate. It's like, yeah.
Okay, and now I see Ted's analogy then. It's just one big needle that stretches all throughout the.
Yeah. So
Gotcha.
yeah, and there's more. There's more. So okay. So that's this one. So the mental model, this is exactly from Stanislav Fort again. So he said a mental model is a web of interconnected high dimensional basins. And so there's again, so that's not exactly what we're describing with the one single canyon, and I'll show you why this is his mental model that's coming up. And it kind of deals with ensembling, so you'll see why I called this the ensembling. So I think we'll probably remember this graph from last time, right? So these are the different initializations. So what we did was like, we took the same network, same data set, we initialized in 3 different points and just ran the optimization. The green one ends up here, the red one ends up here, the blue one ends up here, right? You with me? Yep, okay. So what this one is forget that we did 3, let's just pick one. Let's just look at the green, for example. So what this chart is showing, and again, this is from Stanislav's paper. So what this chart is showing is the checkpoint ID. So this is basically like the epoch number during training, and so is this, right? And so this is symmetric. So you can basically just cut this down the diagonal and just focus on the bottom right or the top left because they're the same, right? So if we look at the bottom right corner, and this is talking about cosine similarity. So if we look at the bottom right corner, that's comparing the 30th epoch, like the weights at the 30th epoch, to the beginning weights, right? So the cosine similarity between a fully trained and a just recently initialized network is very low, right? They're not very similar, right? But then if you come up to the top right corner and you compare the 31st epoch to the 30th epoch, all of the weights are pretty much the same, which is exactly what you'd expect. So this chart probably isn't showing you anything too crazy, right? As you train, it sort of converges to a place and the weights sort of stay similar, right? And this one also probably won't show you anything too crazy either. So again, it's just comparing one trajectory. So let's just focus on green, for example. And it's comparing the same thing, right? Well, it's comparing disagreement, not cosine similarity, but it's looking at epoch versus epoch, right? So here we're at epoch 30 comparing to epoch 0. They disagree on 45% of the elements of the data set, which makes sense, right? This is an untrained model versus a trained model, they're going to disagree, right? And of course, as you get up here in the top right corner, you're comparing a pretty much trained to a pretty much trained, they're going to largely agree, right? And I actually was a little surprised that these weren't darker blue. I was thinking that maybe they could train it a little bit longer, but that's probably not too important. The crazy thing is what happens on the next slide. Okay, so this is comparing. So the X and Y are no longer training epochs. These are independent initializations, right? So like green versus red versus blue. That's what these are. So instead of just green, red, blue, now we have like 25 of them, right? So what this one is this is the cosine similarity of the weights. So for example, if we choose independent solution number 10 and compare it to independent solution number 0, the similarity between their weights is 0, right? And that's kind of what we talked about earlier, is that in such high dimensional spaces, essentially everything is orthogonal, right? So this maybe probably isn't too surprising either, right? It's just saying they are different. And of course, the red stripe down the middle is because they're the exact same as themselves, right? So now the question, this is the weird one.
Wait, no. Yep. It's still comparing 2 different initialization points. No, so green epoch 10 versus red epoch 10 is not automatically going to have similar weights.
No, these aren't epoch numbers. These are independent initialization and trajectories.
Oh, sorry. I'll go.
Good? Okay. So now this is where it gets wild. Okay, so this is the same X and Y, right? So you can kind of think of this vertical line as one of those initializations, right? And one of those trajectories. And then, same with the horizontal. And you'll see the blue, you have 0 disagreement, right? So initialization and trajectory number 10 is the same as number 10. But the crazy thing is everywhere else is disagreeing at about 10%. And these were trained to about 90% accuracy. So what that's saying is that every random initialization, they all get to about the same accuracy, but they all disagree with each other. So it's kind of shocking. So like if we think about, you know, maybe it's just one big basin, right? This is saying it's not, because we're going to different points. Their loss is the same, so they might seem the same, but they are not, because they all disagree with each other.
Yeah, if it were one big basin, they would have the same predictions.
Yep, exactly. So I was pretty surprised about this, and you'll probably remember last talk I kind of showed this, and I was like something, and I talked about the Yannick video. So what Yannick, I think Yannick actually misread this paper in his video. So what he said was these disagreement being at 10% was saying that they disagree on the elements of the data set, right? Like it's getting, you know, number one is getting 10% wrong on the first 10 elements of the data set. And then the number 15 is getting it wrong or disagreeing with a different number, right? But that's not necessarily what the paper's saying, because, you know, let's say they're all erroring at 10%. Let's say model one says like, okay, these last 10% are cars. Model two says they're all cats. They're going to disagree, but they're disagreeing on the same elements of the data set. So this is not necessarily refuting the intrinsic difficulty thing, right? Which is what Yannick was kind of saying, is he was saying they're all disagreeing, and it like the intrinsic difficulty of the data points is not what's causing it, but it might be what's causing it. Okay, so I drew this. I don't know if this will be helpful. Yeah, go ahead.
Yeah, so I'm just wondering, is 10% significant? You know, if it was 5%, would it have been okay? Or so I'm just wondering, like, because we know that there is some variability, right? I was just wondering, like, how much variability is okay?
Well, I think if these are about 90% accurate and they're disagreeing on 10%, that means they're disagreeing on essentially everything. Everything that they're not getting right, they're disagreeing on. Right?
Mm-hmm. I see.
So I would think, yeah, so I think it's significant. And so this is just sort of a little drawing of function space. So this x-axis would be like the image number or the element of your data set. And then the correct answers I made orange, and the guess is green. And if they guess them the same, I made them yellow, because that's, you know, halfway between or whatever. So let's say on this training, you know, it gets all of these right, and then it gets these two wrong, right? So it's 25% error. And then maybe on this training, you know, it gets these same 6 right, it gets these 2 wrong again, but it gets them wrong in a different way. So these 2 disagree, but they agree on which elements of the data set are difficult, and they also have the same loss, right? So these 2 would say like, okay, the first 2 are just hard things to classify, right? But you know, maybe you could also have this one, which would have the same loss. It's also 25% loss, but it's it's getting 5 and 6 wrong as compared to 1 and 2. So this one versus this one would say there's no such thing as intrinsic difficulty. It's just we're all getting something wrong, and it's a different something every time, right? So the paper doesn't say which of these things is the issue, but I think it would be easy to study.
Yeah, it seems like a real key question.
Yeah, I think so too, honestly. And maybe I misread it.
I mean, if you do something like ImageNet where it has like 1,000 different classes, then obviously if you have an image and you don't know what the heck it is, there's like 999 ways you could disagree and both be wrong.
Exactly.
So your first pair, that's really plausible how it could happen for a problem like ImageNet classification.
Yep.
Right? If the latter thing is happening, I'm not sure how you do mode connectivity between that, because at some point you have to flip your predictions.
Yep. That is something I wondered about too, is like, if you followed that trajectory of low, like it's got to be some sort of like gradient between them, right? It's got to be like gradually changing its predictions, I would imagine. So.
Yeah, but if it's just gradually predicting wrong predictions to other wrong predictions, that's not that interesting.
Yeah.
But if it's swapping one right and one wrong prediction, if you move slow enough, at some point you have to, like, you know, discreetly, you can't just smoothly transition in classification. At some point you have to actually flip it.
Yeah. So so I think, so what you're saying is this one seems to make more sense with the mode connectivity thing, I think. Yeah, I agree.
It's easier to see how it could happen. And then maybe you can try some problems other than classification and see if you get the same patterns or whatever.
Mm-hmm.
Right.
Did they also check? Sorry, go ahead.
Nope, I'm done. Go ahead, James.
Yeah, so I was wondering, did they also check like the other ranked classifications? So I'm just wondering, in the cases that it's wrong, the numbers might be so small that, you know, if it guesses cat and it's wrong, and then the second one might be dog, and so the ordering might be off, and the numbers might be quite close to each other, because, you know, it's because we're talking about things that are wrong.
Yeah, I don't know. You're maybe, you know, since it's got to choose something, right? So let's say, you know, it chose this one, and that might just be because this car is at 33%, but cat was at 32%. And since it has to choose something, it has no way of saying, oh, I couldn't really decide, so I just picked one.
Right. And another way to look at it is like, if it is sure, it might be that the top one and the second one have a big difference between each other.
Yeah.
Versus when it's not right.
Now that I think about it, this is done, all this work is done on loss, not accuracy. So loss actually does take that into account, like how sure it is. So I think it would take that into account. But yeah. Okay, so this is also from that same paper. So this, I thought this was pretty telling, right? So let's say you know there's like a blue trajectory and a red trajectory, right? And then the green is the accuracy. So you can see both of these Bayesians we go into are about as accurate as each other, right? But then if you compare the function similarity between the two optimum, you know, here, of course, it's similar to itself. But if you go over here, it's basically the exact same as just any other random point. So they like, there's this thing versus this thing, they're basically disagreeing just as much whether you're in this other minima or if you're in some random place. And the same thing happens over here, right? So they're just as dissimilar to each other as they are to any random spot, even though they both have the same accuracy.
I'm not sure though, Grant, if that's just the definition of similarity in a high dimensional space.
Function similarity?
I'm not sure what this definition, I'd have to read the paper, see what the definition of function similarity is. I'm just saying that, right? If you pick two random points in 100-dimensional space, those vectors are going to be close to orthogonal.
Mm-hmm.
So anything other than itself is going to be orthogonal. And so you're not really differentiating whether there's any pattern to pairs of points in 100-dimensional space. They're either going to be pretty much spot on or they're going to be orthogonal.
Mm-hmm.
So that's just the difficulty of measuring in high dimensional spaces. So again, I'd have to look at the paper, but I just would be curious to see how much of this is based on the difficulty of measurement versus truly, because there are other papers where people have actually said that they were able to, that the weights were not the same from those two different initializations, the red and the blue, but they were able to train something to figure out a transformation of the blue weights into the red weights.
Oh, that's pretty cool.
Right? So some of it could just be permutations. Some of it could be, well, you double one, you have the other, you know, and they cancel out kind of things. Right? So it had to learn those possible things that are ultimately sort of prediction invariant. And they were able to say, like, yes, and I believe the ultimate test was, they said, let me build a brand new model, the yellow model, that has half of the red weights and half of the blue transformed weights intermixed.
Mm-hmm.
And at least on smaller examples, my understanding is they were able to get the yellow model to have not as good, but like not catastrophic, like just small drop off in performance.
Interesting. Yeah, honestly, I'll probably defer to you on this one because I feel like now that I think about it, I think my understanding of their definition of function similarity, I don't think I know exactly how they're using it in that paper. Because
And
I
I'm
don't know
definitely
why.
not putting you on the spot. I'm just saying,
Oh,
I
no,
think it
no, I
would
don't
be
feel
a
like that.
hard problem for any author to define a way of comparing 200-dimensional things to say, how close are they?
Mm-hmm.
Are they truly different or are they not different? Because I think if you just took a 100-dimensional point and you just permuted it, you allowed no other changes,
Mm-hmm.
right? Generally speaking, any test you did would say, wow, these points are really different looking.
Mm-hmm.
Right? And there's 100 factorial different permutations. So like, you know, it's not like
Yeah.
you can easily check all of them to verify whether or not it's a permutation.
Mm-hmm. Yeah. So in any case, I think I'll probably think about this one a little bit more. That's interesting. I think I might have just clicked go back on accident. Yeah. So given that, you know, we have all it takes is initializing from a different place and they're disagreeing, but they're all equally accurate, you know, I feel like the next logical step would be ensembling, right? And so that's actually what this whole paper was about, is ensembling, right? You take different initializations, you train them, they all get just as accurate, but they get just as accurate in different ways, right? So you just ensemble and let them vote between each other. And so that's what this chart is saying. And again, this is Stanislav Fort's, you know, his wording, but he called it like the accuracy versus diversity trade-off. So if you're ensembling, of course, what you want is everything to be 100% accurate. You wouldn't even need an ensemble, right? But if it's not accurate, you at least want them to be diverse, right? So they can vote well, right? Whereas if they're not accurate, but they're all saying the same thing, there's no point to ensemble, right? So what they did in the paper was they tried a bunch of, you know, ensembling techniques, you know, including dropout, right? Which is what some people would say is sort of ensembling, right? And then other people do these like Gaussian type of, I think what they do is, just going off what he was saying, is they find a minimum and then they use some like Gaussian noise to like sort of search the space around it. Again, I don't know too much about that, but in any case, all of these are looking like this. And then boom, up here is those different initializations going to different points, getting the same accuracy, but disagreeing with each other, and then ensembling those. So like, this is convincing to me. I feel like it looks pretty, of course you have to train multiple networks, which is a pain, but it seems to work pretty well.
I'm not sure I'm following this graph. Can you go through that?
Yeah.
Again?
Yeah, please. Yeah. So like this is test accuracy right here, right? So being this way is good, right? And then, so this is the diversity between the models. The prediction diversity, fraction of labels changed divided by the 1 minus accuracy. So over here is, from what I'm understanding, this is basically saying how much do they disagree on the ones they disagree on.
Okay. So is there there's not an ensemble prediction here. This is just comparing the different members of the ensemble, right?
Yes.
Okay.
Well said,
Okay.
yeah. Yep. So if you took all these stars and ensembled them together, would be like the goal, is I think what the paper is saying. Yeah.
Okay.
So do you have that on an upcoming slide, what the ensemble performance is?
I actually don't. Good. Yeah. That seems like a reasonable thing to put in here.
I've certainly heard that ensembling is good and that it tends to yield a better result. I've never heard kind of this description as to why.
Mm-hmm. Interesting. Yeah, I mean, and if you look at this, it sort of makes sense, right? Yeah. So I don't know. I buy it.
I mean, sorry, go ahead. I was just going to say, in the Kaggle world, what I've seen is ensembling allows you to squeeze a few more drops of performance out, but it never really gives you breakthrough performance. So like, let's say it was a really hard problem and you only had 90% accuracy. Okay. Obviously, right, something like MNIST or whatever, you're going to do better than that. But let's say, and so if you built very different models, you said, I'm going to build a ResNet and an efficient net and a vision transformer and a whatever, so that hopefully their, different initializations, different whatevers are truly not correlated. And you ensemble them, you get to like 90.5% accuracy. It's not like somehow the voting from your 10 different ensembles, you're like, well, okay, yeah, majority wins, and now all of a sudden I've got a 99% accurate model. And there could be all sorts of other reasons. That you could have mislabeled training data, and so you're never going to get it right. There could be all sorts of other issues at play here, but I'm just saying, in practice, I have never seen ensembling give you more than just this little bump.
And it sounds like, Ted, you're saying it's a tool when your overall accuracy is relatively low.
No, it doesn't matter where you are. You could be at 99.99, and if you're trying to get one more 9, you can ensemble, or you could be at 52% accuracy and you can ensemble. But it never seems to jump you if you have a good model to begin with.
And
it kind of fits the thesis here, right? Like if they agree, and if they're correct and they agree, ensembling doesn't give you anything.
Right.
If they're wrong, they will end up disagreeing, and so the bump that you can get would be, I guess, small, right?
It's related to the size of where they're wrong.
Oh yeah, so then that would correspond to your first example of how they could differ, is if they're both wrong, it's actually a dog, and they both guessed different things. Neither of them said dog, so they're both wrong. Ensembling them is not really going to help, because you can vote between lots of wrong answers, and you're still going to have a wrong answer.
Yeah,
exactly. I mean, that's what this seems to be saying, is that when they're wrong, you can't really group them together to make them right. Two wrongs.
So what if you do the opposite? What if you got to 90% training accuracy and you did a whole lot of different initializations, like 10,000 initializations, and instead of voting for the one that gets the most votes, you look for the one that gets the least votes? Since they're all wrong.
Because they're all going to be wrong. Yeah,
right.
Maybe.
And I mean, the other thing this is saying is that if something is, on two ends of the spectrum, if something is easy, it's easy for all the models pretty much. And if something is difficult, it's difficult for all the models. They're all going to, and they'll kind of randomly guess if it's difficult, something like that.
I thought Grant said that the paper didn't declare it as either.
Right. Yeah. So I think what I'm gathering now is they're very diverse. So you would think ensembling helps, but what we actually need is not diverse this way. We need diverse this way. And the paper hasn't proved, we don't have proof of that one way or another, right? Yeah, because like Ted said, if there's 1,000 different classes, if you ensemble 1,000 different things together, but they're all just picking randomly, then it's not going to get it there.
I actually have a question.
Yeah, fire.
I somehow feel that if we kind of taking we're training a function that takes n inputs. So if we get some of the local minima, that means that that is kind of combination of the optimum of it's kind of a partially optimum function. So there's kind of some parameters are fit correctly with model, but some are not. So that means that if we get enough correct models, we will be able to predict the zoom that the correct model will follow, right? So all the models that we connect with each other, all the small values are actually kind of like predicting the probable area that all of the parameters reaches their like minimum.
Okay, can you say that one more time?
Yeah,
Sorry.
yeah, I'm thinking that if we so all the best model that we produced at each training is kind of like the local minimum.
Yeah,
As one area, and that is the best fitting of partial. That is at least the best fitting of partly of some of the parameters. So if we want to get the best fitting of all the parameters, I think it's understandable that like it will fall between if we connect if we kind of like circles out all the small local minimas, then we'll be able to get the one that fits the best minimum, right?
Maybe somewhere in between is kind of what you're saying, like
Yeah,
that. Yeah, I agree. Kind of blending them together, right?
Yeah, and it might be that we currently are running into issues of the amount and quality of data that we have. So you may never be able to build, you know, the world's like Uber computer vision model from just 1 million images. It might turn out that that's just far, far too few. Because there is a like perfect CNN that'll get 100% accuracy on ImageNet, but it might not actually have an error that is really low, because you could have mislabeled examples in your training data. You could have all sorts of other garbage in there. You know, these other papers that talk about out of distribution, they talk about ways that things can be, you know. So you have like atypical examples, you have mislabeled examples, and you know, that sort of thing.
So that is why we may sometimes invert some of the parameters to see if there's like a lower minima elsewhere.
I don't know. I mean that's what everyone's trying to figure out. Is there some trick to getting to a better place? And we're trying to understand it, but I don't think yet people have any answers to how to get to a better model. They're just learning little bits more about what's happening, but I don't think we've gotten far enough to say, aha, now do this.
I mean, another way, I guess, to look, I don't know if this is a good way to look at it, is that if the task is difficult or if the example is difficult, even your global minimum will not help you, potentially. And so, you know, if that's the case, then whatever local minima that you find might be good enough.
Yeah. Sort of the intrinsic difficulty thing. Yeah.
Right.
Yeah.
Also, I have a question on this graph. They're dividing by 1 minus accuracy. I was wondering what's going on there, because you've got accuracy. You know, first of all, why are they dividing? And the second is like, you've got accuracy both on the X and Y axis. So I was just trying to figure out what's going on there.
So this is 1 minus accuracy is the number of things that it got wrong, essentially. And this is the fraction of things they disagree on of those. So, right, let's say, you know, it had 90% accuracy. So this is going to be 0.1. And then this is going to be the fraction of the labels that they disagree on. So if it's 0.1 divided by 0.1, you know, that would be 100% disagreement. Does that make sense? Or diversity.
But if you take another example, let's say, you know, one of those pink ones over to the right, like, let's say 0.5 and 0.8. What does that say? So 1 minus accuracy is 0.5. And I can't figure that out.
Yeah, it takes a little thought.
The accuracy isn't shown, Jayanth, so you don't know what it is. For the point that's test accuracy 0.5, that means that it was getting 50% right on the held out test data, right? And
Right.
what 0.8 means is however many of it got wrong, by applying the pink perturbation, whatever that is, rank 4 Gaussian, 80% of the things that it got wrong, it changed predictions on.
I see.
I'm not quite sure what this curve means, but that's how I'm reading the axes.
Right. Okay.
Like, I don't know what this shape means, Grant. Like,
Yeah, I don't know. You mean this shape here?
yeah.
Or what?
But isn't accuracy on both axes? Isn't it the same accuracy, test accuracy on the X and then
This is
1 minus
prediction. This is
accuracy?
diversity.
Right,
Yeah,
but
it's
the
not
formula,
accuracy.
but the formula has accuracy in the denominator, right? 1 minus accuracy. Isn't it the same accuracy?
Yeah, that's the same accuracy, but it's only using 1 minus accuracy as a denominator. It's not.
Correct. So it's like, you know, y divided by 1 minus x versus x, something like that.
Mm-hmm.
Right, except
So,
that something divided by the 1 minus x is the really important thing here. That something is carrying all the water.
Correct. And so this 1 minus accuracy division, I'm wondering what is it doing, because you're using it on both the x and y.
The y, the x-axis is accuracy. The 1
Right.
minus accuracy is just a scale. Okay, so if I have a model that's 95% accurate and I perturb it with one of these things, you're not really going to expect more than 5% of the things to change, because if I'm really sure about the 95% I'm getting right. Whereas if I have a model that's only 60% accurate, then there's a whole 40% of things that I can flip because I'm only confident on 60. So it's just scaling it so that they're all on the same 1.0 scale.
But if you're scaling it by the 1 minus x, you know, it kind of, you're imposing sort of a parabolic kind of shape, aren't you?
No.
Okay.
So like if I said to you, okay, here's a class of 30 students and they took a math test and some got high scores and some got low scores, and I said, freebie, I'm going to let you go and change your answers. Well, the person who got a 95% on the test, you're not going to expect them to change very many answers.
Mm-hmm.
And the person who flunked the test, you might expect them to change a lot of answers.
Right.
So all this is saying is you're scaling how many answers they changed based on how many they got wrong in the first place.
I see.
Well said.
Yeah, that's cool.
And I see we're at time. So I can stop. I have like 3 more that I kind of wanted to show, if that's all right. I think they should be relatively quick, but it's up to everyone. I guess feel free to leave if you want to. Kind of. Okay. So has people talked about double descent before here?
I don't know if we've talked about it. I mean, I'm familiar with it being in the literature.
Okay. Well, I thought it was pretty cool. So like, and again, this is going to be pretty short, but like, if we just focus on this left side first, and it has to do with like, you know, how many parameters we have. So, you know, so this capacity here, so that's, yeah, Roger, that's the way you had defined it, right? So this is like complexity of the model or capacity, right? So this is sort of like number of parameters, right? And so in the typical viewpoint of things is, you know, fewer parameters, we're going to underfit. So we train more, right? And then the word risk is also sort of like error. And then, you know, as we get bigger and bigger, the training error goes down, right? But as we add more capacity or more parameters, this test risk goes up because we begin to overfit, right? Yeah. And so what we're finding now is that if we continue increasing this number of parameters, then it actually drops back down. This test error drops back down again, right? And so they call that double descent, right? So this left hand is like the traditional view from statistics is like, you know, fewer parameters means you generalize better, right? You stop making your model bigger once you get here, right? But here what we're saying is we just keep throwing parameters at it and our model just keeps on getting better, right? And the point at which this switches, which was fascinating to me, was exactly the point at which you interpolate the data. At which point your training loss is 0, right? And so it's kind of weird how this works, and people have kind of thought about it. And I heard Ilya Sutskever, you know, the person from ChatGPT and OpenAI, his explanation of why this is happening is once you're adding more capacity, you know, you're adding more parameters, and once you get to the point at which the number of parameters you have fits exactly the data, then you sort of have a one-to-one correspondence between your parameters and the data. So any tweaking one way or another is going to completely change your model, right? Whereas down here, you know, you have too few parameters. So there isn't that one-to-one correspondence, right? So you're not going to overfit. Now here you have a one-to-one correspondence, you're going to overfit. But now once you get even more, something different is happening, right? And again, basically what Ilya's explanation was, now you have so many parameters that it can read the parameters and it can ignore the ones that don't matter, right? So this one has too few, so there is no one-to-one correspondence. This has just the right number, so your data and your model are completely correlated. Now here you have so many that your model can ignore things that don't matter. That's kind of the thought.
So Grant, so
yeah.
This is specific to transformers or any neural nets with
neural nets in general, yeah.
Okay, I'm assuming, I mean, this OpenAI guy, right? He must be talking in the context of language models, right?
I think the paper is pretty general.
Okay.
But I don't know. Have you seen otherwise?
I think it's an older paper, even before, like, you know, ChatGPT and OpenAI and all that. Yeah. I remember seeing this some time back.
We definitely see this phenomenon in deep learning. It's not unique to just language or whatever. But like, this is not always true. So like if you do polynomial regression, okay, and you do polynomial regression with 50 data points, right, you're going to overfit up till polynomial degree 50, you will then have loss 0. Okay, but as you go to polynomial degree 51, 52, 53, it doesn't suddenly double descent. It just craps out even worse.
But what if you go to 150?
It just craps out even worse. Yeah, it just keeps getting worse and worse and worse.
Yeah.
So this double descent is a function of something. The neural network architecture, the gradient descent algorithm for optimizing, the loss functions that we use. It's something.
Interesting. Yeah, and don't forget the activations, right? The nonlinearities, which don't exist.
Yeah. But you can definitely find counterexamples where over-parameterizing does not do this.
And this is happening during training, not fine-tuning, so to speak, right? This is pre-training. So in fine-tuning, you can overfit, right?
So this behavior happens if you don't early stop. So you just kind of let it train.
So actually, I would say, yeah, with a lot of neural networks, like if you just built a fully connected neural network, let's say you're doing MNIST, right? And you have like a moderate sized 3-5 hidden layer fully connected neural network, you can get this double descent behavior. But you're right. If you keep training that thing, it'll go back up again on the far right beyond where your screen is currently, Grant. So if you overtrain those, they can get slightly worse. They won't get catastrophically overfit, but you will get a worse model with infinite training, so to speak, right? And that's what's kind of interesting about large language models, is that right now that appears not to be happening. that you could just train this thing for 1 billion years and it won't ever get worse. It might not get much better. It might be plateaued, but it won't actually get worse, which is a very nice property to have.
Yeah, so I want to show this slide because I think that's what you're talking about, Ted. So this right here, this is double descent, right? This is kind of the graph. So this is the width parameter, aka like number of parameters, aka complexity in the correct view. Okay, so so what the colors are is the number of epochs. So it takes a little shift of your brain. So like training is not going this way. Training is color. Right? So this is model size, okay? And so what this is saying is, and Ted, I think this is kind of what you're talking about. So like on a huge model, like a language model, its best performance does happen at the highest epoch, right? So you train, and you just keep on training and it keeps getting better and better, which is also what happens when you have too few parameters. But in this regime of this like sort of upward area, like the part of this like traditional view, right? This is where early stopping helps, right? So if you're here and your model isn't big enough, early stopping helps because if you keep training, you're going to come back up here and overfit. Whereas if your model is huge, you keep training and it will never go back up. And these are test errors. So when I saw this, I feel like this graph is kind of fascinating.
So yeah, so I don't know if the models I'm thinking of are in that regime you're pointing to, but like the example I just gave of a moderate sized, fully connected on an easy problem like MNIST, I'm pretty sure your test loss will start to creep back up a little bit.
So that means you're here then.
It could mean that, or it could mean that not all architectures fit this pattern. Because we already know polynomial regression does not fit that pattern.
Grant, I'm trying to see the colors here. I'm not certain.
Is it hard to see? Okay.
But it looks to me like out on the far right side, that it might be that it trains down, loss decreases, then it starts to overfit, but then it comes back down the other side of the hill. So in other words, you have that little hump in kind of both dimensions.
What are you saying?
Reasonable?
You think? Can you say that again?
Okay, so out on the high number of parameters.
Yeah.
I'm wondering if the network, the yellow comes, further closer and closer to the bottom, the blue color, but it looks like there's a sharp shift there, and it should be smooth. So I'm thinking that it actually dips down behind,
comes back up, and then goes back down again.
And then it comes back down to the level.
Yeah, certainly could be.
And that would be consistent. So one of the meetups we had quite a while ago was Tishby, who approached it from an information sharing perspective. And I seem to remember a comment he said that the way they originally discovered this is they accidentally let a system continue training too long. Instead of an early stop, something happened, they didn't stop it, and it ran and ran and ran. And then eventually what they found out is it then actually generalized. The loss came back down and was the generalization was much better at that point.
Very interesting. Yeah. So that might be what you're saying there, right?
I'm not sure if Roger, if you're talking about a paper that you read before I started coming. There was that one paper where they were doing some hard problem. I think it was like some kind of weird math or something like that. But it wasn't a double descent or whatever kind of a thing. It absolutely failed to learn at all. So it was basically just at like random guessing. The model just could not learn. And then the guy went on vacation and forgot to turn off his server. And he let the thing train for a week. And so basically, like, the loss starts out at like 50 and you're hoping it's going to drop down to 1 or whatever, right? And after like 20 epochs or whatever, you know what I mean? It's still at like 49 and it just hasn't learned anything. And it's just like, random guess. And so then only because he went on vacation, they would have never allowed it to run. it just ran and ran and ran and ran and ran and ran. And then all of a sudden, way past the point where anybody would, after like 7 days, all of a sudden it started learning, and then the loss went boom, 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 down from 50 to 2. But it took it forever to start going down. And that was like, what the heck happened here? You know? And I don't know
That sounds like a
is.
similar story. That may be the same story.
Yeah.
But yeah, it was this idea that you train longer than you'd expect. And
right. But in this case, it wasn't really sort of this idea of like, right, like when's the optimal time to stop or whatever. If you had stopped before then, you would have just had garbage. It never actually made progress. So it was like this idea that maybe, you know, Grant, you were showing just like this, the loss surface for like just one single, you know, simple ReLU, right? And if you start way out over on the wrong side, then like maybe you're screwed, right? So maybe for certain problems, they're hard enough that you just start out way in the middle of nowhere. And they were fortunate enough that it followed this ever so slight gradient. And after just days and days of compute, way past when they would have normally stopped it, like it got to the interesting region and then started going downhill.
Pretty cool.
For the large, sorry, I was going to say for the large language models, you know, I wonder if there's so many parameters and there's so much data that is it still in the sort of the downward initial slope that it doesn't even get to like the minima.
Not sure.
Yeah, I don't think we know. I don't think
because you know you got
defining
1 point
for the English language what is right
overfitting.
Like, yeah.
And you know 1 point where I don't know how many trillion parameters, right? So I sometimes wonder if that's what's happening there.
Cool. Well, I think that's a good place to stop if that works for you guys. But yeah, hope interesting, good. Yeah.
Great.
Yeah, that was really interesting.
Yeah, I agree.
Cool. Well, thanks for letting me take the wheel for a little.
We appreciate you taking the wheel for a while.
So Grant, could you either share slides or put together something that has references to the different things that you've talked about, and then maybe we can put that into the description along with the video.
Yeah, I can definitely do that. This was my own notes, but obviously this isn't like detailed enough for someone to like follow a link. So I'll fill in the details here and be good. As you can see, there's
really
a lot
cool,
more to talk about.
I could even see picking one of these, Roger, and going a little bit deeper in a future session.
Yeah, you know, you had a number of references back to that fort. That paper sounds like that could be pretty interesting. I don't know, maybe you've already covered it all in this.
Yeah, I think most of it, at least I skimmed over. You know, we could probably go into much more detail because there's a lot there, and I was kind of just gathering what I saw.
Yeah.